All right. So we did our presentation on rockets and fuel exhaustion. This was done by Jonah Johnson, Preston Lee, Shandu McKinney, Wanling Zhang, and Jiang Wang. And before we start the presentation, I just want to say that the Jonah, Preston, and I will be the people that are giving the presentation right now because the other two could not make it. All right, next slide. Okay, so our problem is that the space inventor Elon Musk enlisted our help to figure out the acceleration, speed, and distance of his favorite rocket, which is the Falcon 9. And we want to figure out the distance once it travels and reaches the end of stage one. He needs this by the end of the presentation or he will cry, and he doesn't need the drag calculated at this time. Next presentation, or next slide. Uh, so we want to figure out the acceleration, distance, and velocity of the Falcon 9 rocket when it reaches the end of the first stage, and that's what we'll be working through. So our assumptions are that the air resistance is, I don't know how to pronounce this word, negligible, and the Earth is not spinning for the duration of the trip, and the rocket is treated as a particle. Rocket thrust is constant, and gravity is a part of our system. And some concepts that we will also include mass flow rate, projectile motion, linear momentum, gravity, and Newton's second law. Next slide. So what we know is the height of the rocket, which is 70 meters, the diameter, which is 3.7 meters, the mass, which is 549,054 kilograms, and the fuel ejected per second is 1,451.5 kilograms per second. Our thrust time per stage engine is 162 seconds, and at stage one, our thrust is 7,686 I don't know how to say that. This
Kilonewtons.
kilonewtons. There we go. Distance from the core of the Earth to the surface is 6,731.009 kilometers. And our unknown is the fuel in the rocket, the gravitational acceleration, velocity at the end of stage one, acceleration at the end of stage one, distance from the surface at the end of stage one.
So to start off our problem, we got our two schematics. The rocket on the surface at the beginning, and the rocket right when stage one ends and stage two is supposed to start. So in stage one, or the initial...
Sorry.
You're good. The only thing we really have is normal force and gravity, which we don't really care about, which they suck. And the final is we have to prove that thrust is bigger than gravity in order for velocity and acceleration to be going upward. Hence in the schematic. Next slide. So we have a bunch of variables here. So we got m, the mass of the rocket, m dot, which is the mass flow rate, which is the mass of the rocket exhaust exiting. The velocity of the rocket is v, a for the acceleration, v exhaust, or exh, for the velocity of the exhaust exiting the rocket, t for the thrust of the rocket, and it is the momentum given to the rocket's exhaust gases, which is equal to the momentum of the rocket in the opposite direction, which gives us the thrust equation, which helps allow this to be a linear momentum problem as we are conserving linear momentum with gravity being a part of the system. Then RE is the mean radius of the Earth, D or H, distance from the surface, and we're assuming that the forces in Y is everything in the rocket. All the forces we need to calculate, as we are only doing the stage one of the rocket. So we got 7 equations we've used. The final velocity equation, which is initial velocity plus exhaust velocity, is the natural log of mass initial over the mass at that time. And then we got the acceleration of gravity at a given height, the thrust, which we assume is constant, the sum of the forces in the y direction. We got the acceleration equation, the mass flow rate equation, and the distance equation. So starting off with the calculations, we already know the mass of the rocket, which is given to us. And then we can quickly figure out the mass of the rocket exhaust that's already exited, because we're only calculating the velocity, acceleration, and distance at 162 seconds, which gives us an ME of 235,143 kilograms. Then thrust is also given to us as 7,686 kilonewtons. And then on the right, you can see with the concept of linear momentum, it allows us to have that simple velocity equation. And then continue on with the calculations. We can quickly find out that what we need to find is the velocity of the exhaust gases, because we're given the mass initial, and then we can make the mass final at that given moment in time, dependent on time. And we already know m dot, and we know thrust, and with that handy general thrust equation, we can figure out that the exhaust velocity, which is constant, is 5.295 kilometers a second, which gives us the velocity equation.
So now going through all of the different equations, I wanted to use some kind of software that would allow us to plug in all the equations and see all of the outputs at any given time. So I used Desmos for this. So you can see the equation of gravity, you can see the equation of height, you can see the variable of time, you can see the equation of the sum of the forces in the y, you can see the equation of acceleration, and you can see the equation of final velocity. And here we have it at its initial state. Obviously, you only have gravity and the weight of the rocket. And then in final, you have the change in gravity, because as you go further from the center of the Earth, gravity changes. So we had to take that into account. We have the height in kilometers or kilometers. We have the time in seconds. And this is the force at the final time of 162 seconds. This is its acceleration and its velocity. And I actually have the simulation up, and I will demonstrate that at the end of the presentation. And then kind of looking over, is this realistic or not? It can't be realistic to a certain degree because we didn't include drag or air resistance. And we are assuming that the Earth is not rotating, because when you include the rotation of the Earth, the rocket doesn't go up in a straight line. And there is a small change in thrust due to the pressure as the rocket travels higher in altitude. And also, there's also other factors such as engine efficiency, which decreases as a rocket gets higher in altitude. But one thing that was really cool is that our scenario, our final height, is actually really close to the Earth's atmosphere from one of the websites that we have cited. So what the website basically stated is that Earth's atmosphere is about 480 kilometers thick, but it also says that there is no exact place where the Earth's atmosphere ends. It just gets thinner and thinner until it merges with outer space. So we did a lot of looking into that and what that means. There are some things that say that Earth's atmosphere is 10,000 kilometers thick, but I think based off of the website that was talking about rockets and space, that first height there, that 480 kilometers, is more like the height that you need to reach as a rocket is traveling into space. And so it's kind of cool that our rocket basically met that space or met that height. So to conclude, we kind of did rocket science. We found some of the forces in the y direction, and we also found displacement at our final time and actually at any given time because of our simulation that we made. And we can find acceleration at any time and velocity at any time. But for our final time, we have the distance of 479.58 kilometers. We have our acceleration of 3.958 kilometers per second, per second squared, that should say. And we have our velocity of 2.96 kilometers per second. We have a bunch of sources. And then to look at the simulation, it's just here in Desmos. We can change the time to any given time. I have it set between 0 and 162 seconds. But as you can see, we can go at any time and find what the rocket's acceleration, velocity, and height is, as well as the effect of gravity at any time.